Good morning, students. Today we have to discuss process management, process descriptor, and the task structure. Following are the major topics associated with the lecture: process management, process and threads, life cycle of process creation using fork system call, parent process and child process. Starting from the process management. We have already taken the particular concept in prior where the process definition has been discussed. A process is usually defined as an instance of program in execution or a process in a program in the midst of execution. Uh, Executing program is somewhat known as process. A process is said to be born when the program start execution and remain alive as long as the program is active. This is the very first part of life cycle of process. After completion of execution, the process is supposed to be die. That is what is known as termination of process. A process also has a name, usually the name of the program being executed. For example, if you are executing grep command, a process named grep is created. When we open terminal for executing commands, a shell process is immediately created with the shell name like bash, csh, ksh or bourne shell. And if you are executing a program with C language, then the name of the program is becoming the name of process. Processes are, however, more than just executing programs. They also include a set of resources such as open file. A process may open file and pending signals, internal kernel data, process state, and address space or more threads of execution, and data section containing global variables. Now, if we are talking about comparison of process and thread, a thread can be considered as lightweight process. By definition, a thread is an execution of context or flow of execution in a process. Thus, every process consists of at least one thread, but it might be possible that a process may have more than one thread. A process containing several execution threads is said to be multi-threaded process. Having more than one thread is process enabled concurrent programming, and on multiprocessor system, true parallelism is existing. Each thread do have its own thread ID. As you have already gone through the process identification with the help of PS command, each thread do have its own thread ID also, program counter, process tag, and set of registers. The kernel schedule individual thread, not process. At kernel level, we do have kernel scheduling, not process scheduling. Process scheduling is associated with the operating system. What makes threads specially useful is that they share an address space between each other, avoiding any kind of inter-process communication channel to communicate. Dear students, if you have gone through the operating system syllabus or course, you might have gone through the concept of process lifecycle. Every process starts executing, it remains executing or in running state, and after that it may pass on to other type of states such as stopped or waiting or any other state. The process lifecycle diagram you might have gone through in operating system. A process which starts by Linux system is generally considered with the help of user programming with the help of fork system call. That system call generate a child process in the parent process. If you are looking at the third point, the process that called fork is the parent, whereas the new process is called child. The parent and child generally considered as a replication of each other. or you can say the child process is replication of parent process. And whatsoever outcome is there, that is very much similar type of outcome. The only thing is that we have to check out the child process do have separate ID other than the parent process ID. The parent process ID is somewhat positive in number, whereas child process ID is 0 generally. A process is considered to be terminated with the help of exit system call. This function terminates the process and frees all its resources. Resources can consider CPU or memory. When the process exits or terminates, it is placed into special zombie state that is used to represent the terminated process until the parent call wait or wait PID. A zombie process is one which supposed to be terminated, but it do not release the resources which is acquired by it during the execution of the process. Thereby, if you are looking at fourth point, the process in zombie state are also called zombie processes that terminate, that is terminated but not free up from the address space. They are still occupying the address space but yet are required to be terminated. A parent process can inquire about the status of terminated child via wait system call, which enable the parent process to retrieve the information about the child termination. That means if a parent invoke any child process, then the child should terminate with the exit system call. If that is not being considered by the child process, then the child process become zombie process. And parent can inquire about the status of the terminated process with the help of wait or wait PID system call. If we are taking the concept of process creation, then that can be taken up with the help of fork system call. The fork system call creates a new process which is an almost exact duplicate of calling process. That is, the calling process is termed as parent process and the called process is termed as child process. And the child process is a replica of parent process. They are distinguished by the value returned by the fork. The fork generally return the process ID. If you are looking at the last line that represent the declaration of fork, that used to return the PID underscore T, that is the process ID value of the child process at the particular call. The diagrammatic representation of fork system call is given as follows, where we are displaying the parent process, child process, and associated element with respect to the individual processes, and they may refer to the inode table and file table for opening file, current directory, and change of root. Other than this, kernel stack is there that used to maintain the information about the variables and other type of data structure. Child data is mentioned in the child process and parent data is mentioned in the parent process. And other associated information can be managed at the each individual process level. If we are looking at the return values of the fork system call, that used to return three type of values. It can be -1 in case if child process was unsuccessful or parent process is unable to create the child process due to the unavailability of the resources or permissions. A fork may return zero value that is associated with the newly created child process, and if necessary the child can obtain its own ID by using getPID and parent ID using getPPID function. The fork system call can also return positive value that is associated with the parent process of the child process. The PID underscore T can be considered for storing the value of the fork system call in the form of variable. It is generally represented in the form of integer. Otherwise, we can take up the integer value also, but PID underscore T is defined in sys slash types.h file. If we are looking at the few important points associated with the fork system call, every child process is somewhat very much identical to the parent process, but the few necessary differences are highlighted over here. The very first one is the PID of child is of course newly allocated and different from the parent. Generally it is 0. The child parent ID, parent PID is set to the PID of parent process. That means the PPID of child process, that is parent process ID of child parent is parent process ID. The resources statistics are reset to 0 in the child. Any appending signals are cleared as in case of parent process fork system call exists, but child do not invoke fork system call on its own and not inherited by child. Any acquired file lock are not inherited by the child. There are two type of errors mentioned over here. If you are having -1 value return, that means fork is not able to create the child process. And if you are having following possible outcome, E again, the kernel failed to allocate the certain resources such as new PID or R limit and proc resource limit has been reached. The second is E no mem. In case of insufficient kernel memory was available, then the following type of error can be retrieved. These are given in the capital letter as these are mentioned as constant in the header file. This is sample program 1 for fork system call. In the given program, we have simply printed hello world outcome, and the outcome of the program will given twice print value, one from the parent and one from child. The given program will work as parent, and fork system call will provide you the replica of same program in the form of child process. But in child process, the fork will not repeat itself, only print command will work for the specific outcome. If you are looking at the execution of this particular program, the part which we have discussed over here, the very first one is program itself. The second part which is given over here, I am highlighting it, that is compilation command, that is gcc f1.c. F1 is the name of program and gcc is the compilation command. After compilation, if you want to execute the program, the outcome file in the binary format will be available in a.out, and if you want to execute the compiled outcome, in that case you have to specify ./a.out for execution. And in execution, the outcome will be hello world, that will be printed twice. That is because one from parent. Now, process if you are looking at from child process, which parent process where I have made 3 fork system call invocation in the main function, the outcome after compilation will comprise of 8 hello prints. The one from parent and other 2 fork will be invoked from the first level child program, and after that in the third level again you will have 3 call for the third level. In totality there will be 8 outcomes from the parent to child and next level child. The 8 outcome will be available over here. Again look at third program, where we have defined a separate function other than main function, that is fork example. Within that we have tried to invoke fork in if condition, and if it used to return value 0, then the given process is child process, otherwise it is parent process. From main we are calling fork example, and after that if fork return value other than 0, then the else part will execute and print hello parent, hello from parent. And if it used to return zero value, then you are going to get the print as hello from child. The execution of this particular program may generate any of the particular outcome either from parent or from child. There is no predefined outcome sequence. Anything can be printed on the screen first, either from child process message or from parent process message. This is another similar type of example I am giving over here, where you can get the process ID by using getPID method. And again, if you want to check out whether it is parent or child process ID, in that case you can compare it with the zero value. And if zero value do appear in the return, in that case it is child process, otherwise it is parent process. In the last program, we have seen PID underscore T data type that used to store the process ID of the program or process. This particular type is available in systypes.h header file. It is nothing but an integer type of data which is defined with the help of typedef statement available in C. Dear students, this is most important part related to process, that is process descriptor. In every operating system, each process is represented by a data structure that used to hold the information related to the process. The generic name of that data structure in Linux is PCB or process control block. If you are looking at second point, in Linux, each process is represented by two main data structures. First is PCB, which is the data structure name of name struct task underscore struct, and second one is a struct thread underscore info. The PCB struct task underscore struct holds most of the information of the process, also called process descriptor. The struct thread underscore info contain low level information of the process. The kernel stores the list of processes in a circular doubly linked list, which you have worked out in data structure. Similar type of things you are implemented at the operating system level for managing the information related to process. That means if you are going in the system programming, in that case you must be aware about the usage of data structure and how you are going to manage the data related to processes. If you are looking at the last part, the process descriptor contains all information related to single process like process ID, state, parent process, children, sibling, process register, open file, address space, and process priority, etc. As discussed in the last slide, the task underscore struct data structure do not contain entire information associated with the process. Rather, it contains pointers, where other type of structures used to handle the process information. The entire information related to various processes is managed in the help with the help of circular doubly linked list for information management related to processes. The head of the linked list is containing the init task descriptor, which is the first element of the list, the process 0 or swapper process. The task struct is a relatively large data structure at around 1.7 kilobytes on a 32-bit machine, and on a 64-bit machine structure may be different. This size, however, is quite small considering that the structure contains all information that kernel has and need about a process. The process descriptor contains the data that describe the executing program, open files, and process address space, pending signal, and the process state, and much more. And this type of information is placed in the task struct. The diagrammatic representation of Linux process descriptor is given over here, where we do have some pointers also which are pointing towards various large block for maintaining the information related to processes. The various fields associated with the task struct are described over here. You can go through them and check out what is the purpose of the particular field. As the name and description is automatically understood by the user, you can check out, and if you do have any query you can ask. We have already gone through some process related command uh, in our previous lectures. There are two type of processes. One is foreground processes, which are basically interactive type of processes. User can directly get the display of those processes on the terminal itself, and some processes are background processes which are running in the background, or some scheduled processes can also be there, which we have gone through with the help of add command. Add command is specifically meant for scheduling the processes at a particular time, and you can check out how you can bring the background process. For that we have already discussed a few command in the lectures which we have already covered up. If we want to run a process in the background, we can add ampersand sign at the end of the command, and if we want to bring it in the foreground we can give fg command. We can also use bg command for doing the same. For terminating a particular process we can use control c command also, and for sending control terminal to all the processes we can give cgup. That's all for today. Thank you. If you do have any query you can revert back to me on WhatsApp or mail. Thank you. Have a nice day.